Okay, so the second talk will be by Neil Strickland on ambidexterity.
Okay, thank you. So first let me just thank the organizers for inviting me to this wonderful place. It's been a very interesting meeting so far. So I'm going to be talking, as I say, about ambidexterity. So I'm going to be using slides. So you can, my slides are on the web here. You can see it's strickland1.org. And slides, first couple of talks. There's also various kind of background documents that you might find useful here. So there's some general introduction to spectra and some stuff about formal group theory that's going to be relevant for Morava E theory and so on. Going to be making some slight use of theory of infinity categories as a sort of general framework for talking about homotopy theory. So there's got a slides from an introductory talk about infinity categories, in case anyone needs to read a little bit about that. And then also I've got an introductory talk about chromatic homotopy theory. And then the sort of background literature on ambidexterity, a few papers here, starting with Greenlees and Sadowski in 1996, up to this work of Carmeli, Schlank, and Janowski in 2018. Okay, so that's what it's about. Ambidexterity refers to a situation where you've got functors that are both left and right adjoint to each other. Or, that's kind of one way to think about it. Or you've got a functor which has got a left adjoint and a right adjoint, and they're isomorphic to each other. That's kind of the same sort of thing. And we've already had in other people's talks kind of things somewhat similar to this. You've got Serre duality is a situation where you've got a left and a right adjoint that are the same except up to some kind of twisting, or kind of a Gorenstein local duality thing where you've got a left and a right adjoint that are kind of the same up to cellularization or some other kind of adjustment. But we're going to be just focusing on cases where left and right adjoint are actually just isomorphic. So today we're going to be, we'll spend some time looking at some fairly elementary examples because they kind of set the scene in a useful way and make it easier to understand what's going on later. So easy example is going to be related to functors of finite groupoids. So let's just remember what's a groupoid. A groupoid is a category in which all morphisms are isomorphisms. So most obvious example of that is if you've got a group. A group is you can consider as a category of one object, and all the morphisms are isomorphisms. So saying things about finite groupoids is, it can basically anything you might want to say about finite groupoids, you can reduce if you want to statements about finite groups. And for some purposes, that's kind of convenient to do. But it turns out that many things sort of just become more natural if you formulate them in terms of groupoids. And especially if we want to build up to the kind of final thing that we're supposed to do, there's kind of chromatic examples of ambidexterity in the context of finite infinity groupoids. And so to build up to that, it's kind of useful to talk about normal groupoids first. So we're going to have some finite groupoids, G and H, and a functor Q from G to H. And we're going to look at representations of finite groupoids. So groupoid is a category, and we've got this category curly V. Curly V is going to be the category of complex vector spaces. And VG is the category of functors from G to V. So, if G was just a group, then this functor category would just be the category of representations of G. So, and then similarly, if G and H were both groups, then say you've got a functor of finite groupoids. That's in the case where they're just groups, it just means you've got a homomorphism of groups. So. So now if you've got this Q, then it's going to give you a functor from representations of H to representations of G, just kind of pulling back along Q. This composition with Q gives you a functor like that. And it's a kind of very formal, you've got left and right adjoints to this. Existence of left and right adjoints is kind of usually not a big deal. Just have to have enough limits and co-limits in the relevant categories. And so it's pretty formal that you've got both a left adjoint and a right adjoint. It's kind of less formal that there's a morphism between them. So we'll spend a little while later to explain why there's a morphism from the left adjoint to the right adjoint. And then we're going to need to prove that it's actually an isomorphism. And this is actually reduces to kind of very familiar things in representation theory of finite groups. But like I say, as a warm up to things we want to do later, we want to cast everything in the language of groupoids. So there we were doing kind of complex representations, but we could do it just kind of with Z-linear representations instead. So curly A is going to be our category of just of abelian groups, and then again you've got this category AG or functors from G to A, the category of Z-linear representations. These are allowed to be torsion groups, of course, and don't have to be free abelian. And once again, just you've got a functor from G to A, and then you compose, sorry, you've got a functor from H to A, you just compose it with Q to get a functor from G to A. So that gives you a functor Q upper star from AH to AG, and it has left and right adjoints. And in the same way, you've got the natural map nu from the left adjoint to the right adjoint. And so you want to prove that nu is an isomorphism, but you can't in this case. To prove that nu is an isomorphism, so I should go back actually to this statement in the complex case. I mean, kind of a key example of what's going on here is this fact that if you've got a complex representation of a finite group, then the co-invariance is isomorphic to the invariance. And you can write down the map from the co-invariance to the invariance quite easily, and you want to prove that it's an isomorphism. But to prove that it's an isomorphism, you need to divide by the order of the group. And because we're working over Z, we can no longer guarantee to do that. Okay, so in this context, it's certainly not true that this nu is always an isomorphism, but sometimes it is. I mean, sometimes because here. The thing about invariance and co-invariance, that's basically looking at the case where you've just got the, H is just the trivial group, and you've got the functor from G to the trivial group. That's the case in which the invariance and the co-invariance are relevant. And there you have to divide by the order of G. And that's the order of your G. Of course, in that case, that's the kernel of your map from G to H. But if you think about, in this more general thing, you've got a functor Q. Well, basically, you have to divide by the orders of some kernels. And if your Q is faithful, then those kernels are trivial, and you don't have to divide by anything. So it ends up being the case that if Q is a faithful functor, relevant orders of 1, so you can do this proof that the left and right adjoints are the same without having to divide by anything. And so you get the left adjoint and the right adjoint are the same. And there's also a kind of slightly different thing. You could, instead of looking at the full category of all representations, you could look at the ones that are projective. Projective objects in, this curly AG, of course, is an abelian category. And it's basically representable functors will give you projective generators here. And if you restrict attention to your projectives, then kind of slightly different sort of argument shows you that in those cases, the left and right adjoints are the same. Okay, so that's all kind of very classical. Let's do something just a bit more complicated. We're going to do spectral representations. In other words, functors from your category G to the category curly S of spectra. Review a few things about this already, but well, I guess you've already seen. Priyanka told us some stuff about S, and Constanza's told us lots of stuff about S as well. Yeah, here we're going to look at this, and we're going to look at it as an infinity category. You could get away without using infinity categories for these kinds of things. You could do model categories or topological categories or more classical kinds of foundations, but realistically, most of the kind of current literature on anything in chromatic homotopy theory is written in the language of infinity categories. So it's good to just try and start to get used to that. So we're going to talk in terms of infinity categories. So you've got your groupoid G, and SG is a category of functors from that spectra. And it's you know, again, very formal that you get this map Q, this functor Q upper star from spectral representations of H to spectral representations of G. And then you want to say that it's got left adjoint and a right adjoint. And you do have to be careful here that we're now, I mean, yeah, if we should treat SG as a category in the ordinary sense, then you can do these left and right adjoints by making limits and co-limits. That's not quite what we want to do here. We want to do what's effectively doing homotopy limits or homotopy co-limits, which is the same as doing, you know, what are called limits in the infinity categorical sense. So, yeah, so there's some technicalities to go through if you really want to do that properly. But it is kind of all wrapped up in the sort of general framework of infinity categories. And once you sort of get used to the framework of infinity categories, and the story about limits and co-limits there is kind of similar to the story about ordinary limits and co-limits in ordinary categories, once you kind of get your head in the right place. Then we, yeah, so we've got this, and then we need to define, so you're going to have this left and right adjoint, and again, you want to define this nu. And now, so it's going to be, there's going to be a bit more to say about how to do nu in this spectral context. And this is, we'll begin to, we'll have to begin to start talking about the construction called the transfer, which a bunch of things. But again, it's going to work out that in the case where Q is faithful, then this nu here is going to be an isomorphism. That's essentially what's known as the theorem of Wertmuller in equivariant stable homotopy theory. And we've heard various things about kind of Tate constructions in John's talks. Tate construction is more or less the, it's just going to be the cofiber of this nu. Your S is curly S, remember, is a triangulated category. You've got a morphism in a triangulated category. You can fit it in an exact triangle, the third term of which is going to be, so it's the cofiber of your map. And the map's an isomorphism if and only if its cofiber is trivial. And so we're wanting to say that this nu is an isomorphism. That's kind of, it's equivalent to saying that the cofiber is trivial or the Tate construction is trivial. This kind of this theme of the Tate construction coming up is going to be something that comes up a lot. Okay, so those were kind of again still reasonably elementary examples, things that were known a very long time ago. But now we're going to start doing some chromatic stuff. So as usual, we're going to fix a prime p and a height n, and we've got these Morava E theory and Morava K theory. So we'll, Constanza said some stuff about these kinds of things already. We'll review, well, I think not in this talk, but in later talks, we'll review some of the relevant stuff about K and E. And then, so we've got this Morava K theory and Morava E theory, and we have curly K is going to be the infinity category of Kn local spectrum. So this is the kind of category that you look at when you want to know everything about stable homotopy theory that's kind of visible to Morava, and you want to discard any phenomena that are not visible to Morava K theory. So it's kind of like working with a localization or a completion of a category of modules. So that's the category we're going to work with. And so again, you can have representations of a finite groupoid in this category curly K, and you've got your pullback functor, the left adjoint and the right adjoint, and there's nothing new yet that we can. It's the same as with general spectra. We've got this transfer map from the left adjoint to the right adjoint, and the cofibers is Tate. But there's a kind of in this context, the Tate is 0. And this was a theorem of Greenlees and Sadowski that, at least the key part of it is this is the theorem of Greenlees and Sadowski, which says that you take this, this Morava K-theory spectrum and you apply the Tate construction to that relative to a finite group, then you're going to get 0. Now that's kind of the heart of it, but once you prove the one kind of Morava K-theory Tate spectrum is 0, then you can prove that a whole bunch of other kind of things that are mixtures of Tate theory and Morava K-theory, they're also 0. Okay, so that's that. Okay. So that's that was for G being a finite groupoid. But yeah, we do want to do this kind of framework of infinity categories. Yeah, so in this framework, infinity groupoids are the you've got this thing called these things called infinity categories, and just as amongst categories you have groupoids where all morphisms are isomorphisms. You also have infinity groupoids as a kind of special case of infinity categories, and it works out though that the category, the theory of infinity groupoids is just the same as the homotopy theory of spaces. This is kind of a central reason why this kind of framework of infinity categories is an excellent formal framework for doing homotopy theory and things related to homotopy. And and a groupoid G is kind of a well, it's an ordinary groupoid. That's a special case of an infinity groupoid. And the way this kind of relates, we say groupoids, infinity groupoids correspond to spaces, but via this classifying space construction. So the if you've got an ordinary groupoid G, then you take its classifying space BG, and that's a space which corresponds to an infinity groupoid in the framework of Lurie, and that's how it fits together. So there's always kind of a little bit of a kind of linguistic ambiguity about whether you're talking about G or BG, but just have to get used to that. Yeah. So infinity groupoids are spaces. What do we mean by a finite infinity groupoid? Well, it has to be what's known as a pi finite space. So pi finite space, well, it has to be, you've only got finitely many path components. No, that's all n, but for ordinary groupoids, well, actually they said it for groups as opposed to groupoids, but yeah, that's just a very tiny translation, but groupoids rather than infinity groupoids. Yeah. And so to say, well, got a space, you want to say, well, what it means for it to be an infinity groupoid, so to be a finite infinity groupoid, well, so it's got to have only finitely many components, and then each component is supposed to only have a finite amount of homotopy groups. So I've written it this way: the order of the product of all the homotopy groups is finite, which means that if you go for k sufficiently large, then pi k of x will be trivial, and also each individual pi kx is a finite group. So and if you take the classifying space of an ordinary groupoid, then pi 2 and higher will all be trivial, and pi 1 is just the kind of automorphism groups in the groupoid G. Okay, so that's what we mean by finite infinity groupoid, so I'm going to use kind of slightly different notation, which is supposed to sort of reflect the fact that we're moving between G and BG. So curly K of X is that's you should think of this as families of K local spectra continuously parameterized by the points of X, and that's so that's one way to think about it. But we can also say we can think of X as being an infinity groupoid. Well, the groupoid is a kind of category, and curly K is a kind of category. So we can think about functors from our infinity groupoid to K, and these things are the same. It's kind of it's all sort of built into the whole infinity categorical picture that functors from a space considered as an infinity groupoid is the same thing as local systems or parameterized families. So we've got these two different pictures of this category curly X. curly K of X. But again, we've got this, suppose we've got a functor of infinity groupoids, but let's say it's not just the objects, but the whole kind of category of infinity groupoids is the same as the category of spaces, essentially. So if a functor of finite infinity groupoids is the same as giving a continuous map of high finite spaces. Okay, so so if you've got one thing like this, well then you've got this Q upper star construction from curly K of Y back to curly K of X. So, again, as we had on the previous slide, if we're thinking about this as curly KX as a category of functors, then this is just a composition with Q. On the other hand, if we think about this as being parameterized families, well, you've got family parameterized by Y, and then you've got this Q from X to Y, then you just, the thing at a point of X is just what you get. Apply Q and look at the fiber at that point of Y. So we've got this pullback functor that we can think about in various different ways, but as usual, it just has left and right adjoints. And so there's this kind of big theorem of Hopkins and Lurie that in this context, the left adjoint and the right adjoint are again equivalent. And the kind of structure of the proof is kind of quite interesting. It's by induction on the truncation level. So what do I mean by the truncation level? So I said here, we're saying that you've got, I want to say that a space is pi finite, then homotopy groups have to vanish past a certain point. So that's the truncation level. So ordinary groupoid, you take a classifying space of an ordinary groupoid, it has a pi 1, but it doesn't have a pi 2 or a pi 3 or something. So you kind of say that that's at truncation level 1. Got a space which has up to pi 10 and then pi 11 and higher 0, then you can say that's at truncation level 10. So we do this by induction on the truncation level. You do have to start at m equals 1. There's this kind of there's this inductive method which doesn't work to get between m equals 0 and m equals 1. You do have to start with the thing that is proved by completely different methods in the last millennium. But then and from m equals 1 upwards, there's a kind of a uniform inductive procedure. But an interesting feature of it is that it's not like totally formal that we should have this map nu from the left adjoint to the right adjoint. And if you want to define nu even at the next level, you already need to know that nu is an isomorphism at the previous level. It's a kind of interesting feature of the way this kind of fits together. And so what's kind of happening? What's the difference between one truncation level and the next? If you've got if you've got a space that's a truncation level m plus 1, so it's got a pi m plus 1, but nothing higher than that. And so the difference between that and something at the previous truncation level is just, in some sense, something which has only got a pi m plus 1. A space with only a single homotopy group, that's what's called an Eilenberg-MacLane space. So you've got you need to kind of think about the properties of Eilenberg-MacLane spaces with single homotopy group in degree m plus 1, and that single homotopy group has to be finite because we're looking at pi finite spaces here. So a kind of key issue is to understand about the Morava K theory and Morava E theory of these Eilenberg-MacLane spaces. There's a whole story about that in terms of exterior algebras generated by formal groups, or Dieudonné theory, which probably come up in the third or fourth lecture of most likely the fourth lecture of this series. Also say a few words about telescopic versions. That was a as this we consider this category curly K. Remember, K was our Kn local spectra, But there's a slightly larger category, curly K prime, of telescopically local spectra. There's this, Constanza mentioned the telescope conjecture. Telescope conjecture is, can be formulated in many different ways, but one way you can formulate it is it's equivalent to saying that this K is equal to K prime. But we don't know whether K, so let's maybe take a minute to talk about that. Okay, so so there's this whole story about Hopkins-Donat-Smith nilpotence theory. Okay, so let's say it this way. So there's this Brown-Peterson spectrum. And the coefficient ring of Brown-Peterson spectrum, P locals, so, and this kind of controls all sorts of things about chromatic homotopy theory. So one of the theorems that comes out of this nilpotence theory is that so for any n, we can find a finite spectrum. Let's call it Fn. BP star Fn of the form so here you've got these polynomial generators starting with V1, but you also have this V0 is just a number P. And so, so theorem says that you can find a finite spectrum where the BP theory is of this general form. In fact, you can find lots of these. I mean, you can't choose the I's in a completely arbitrary way, but if the I's are large enough and divisible by sufficiently large powers of P, then you can do it. Okay, and you also find a map V. Then you can find a self-map V of some high degree here, such that the effect of V on this BP groups is just multiplication by some power of the next thing, right? You've killed off powers of V0 up to Vn minus 1, you've still got Vn, and then this map is going to be multiplication by some power of Vn, and so your Fn plus 1, you're going to take the co-fiber of this. Okay, so you've got these Fn's, and then so let me use this notation. I'm going to call K prime n is Vn inverse Fn. So this is the homotopy co-limit of Fn So once you've got this V, you see is, well, I mean, you could take the cofiber of V to go the next thing, Fn plus 1. But instead of taking the cofiber, you could instead take the telescope. You could invert this V, which is going to be the same as inverting Vn minus 1 because it's kind of just acting as a power like that. And so you've got this BP star Kn prime. And then, so curly K prime is the one way, yeah, several different ways you could say it, but one way you can say it is that this curly K prime is the category of spectra that are kind of local with respect to this. And, and to sort of kind of make this curly K prime look similar to actually, here's a good way, better way to say it. Yeah, so this is a theorem. You can check that curly K is the category of spectra local with respect to BP smash Kn prime. I mean, this K was originally defined to be spectra local with respect to Kn, but it turns out that Kn has the same Basu class as this smash product here. So that should make you think that the curly K and the curly K prime kind of look rather similar. And Ravenel conjectured that they were the same, and no one knows. Yeah, so to say, I mean, there was this paper in 1984 by Ravenel, which had a whole bunch of conjectures in. And this Hopkins-Devenat-Smith nilpotence theory was basically the resolution of all of those conjectures apart from the nilpotence conjecture. And that was kind of that was the whole foundation of chromatic homotopy theory. It was an enormously productive and fruitful thing, but they didn't manage to prove the telescope conjecture. And then a lot of people kind of came to the conclusion that the telescope conjecture was probably false. And so there was kind of several large efforts to prove that the telescope conjecture was false, but again, they kind of failed. I mean, there was, roughly speaking, the way it was is that people came to the conclusion that for the telescope, they could write down a certain spectral sequence with a very large E2 term, and for the telescope conjecture to be true, there had to be some kind of extremely surprising and complicated pattern of differentials in the spectral sequence. They didn't believe that it was possible to have such a pattern, but they weren't able to prove that it was inconsistent. Okay, so it still remains open. I mean, I have heard people spreading rumors recently that maybe some people may be able to disprove it, but well, we'll see. But anyway, so but because we don't know whether K is equal to K prime, if we prove theorems for curly K, then we don't know that they're proved for curly K prime. And in fact, so you have to. It's a somewhat different collection of methods that are available for proving things in K prime, partly related, partly not. Anyway, so there was this, the Greenleaf-Sadowski thing proved, I think it's in 1996. A telescopic analog of it was proved by Nick Kuhn in 2003. And then recently, Karmeli, Schlank, and Janowski, they proved the telescopic analog of the Hopkins-Lurie ambidexterity theorem in 2018. And in fact, these three and they're kind of other people in the same circle have actually, they proved a whole bunch of new stuff generally around the same circle of ideas of ambidexterity in the last few years. Okay, so let me make some comments about the relationship with the Thiers-Seagull theorem. Okay, so So we've said various things about functors between finite groupoids. One kind of functor that you have always is just a functor from G, unique functor to 1. 1 means the terminal category, a category with only one object and one morphism. And so the, in here, for this case, your left and right adjoints to the C upper star. I mean, yeah, C upper star is just kind of takes an object and gives it the trivial G action, or takes an object and gives you the constant functor with that value. And left and right adjoint to that are just homotopy and homotopy colimit, homotopy limit functors. As we'll explain a bit later, I mean, we've said various things about an arbitrary functor of finite groupoids Q from G to H. But almost any question that you might have about the left and right adjoint Q shriek and Q star for that Q, they can be reduced to questions about these kind of homotopy limits and colimits by this kind of Kahn formula. I'll spell that out a bit more later, but the Kahn formula allows you to calculate all of these left-right adjoints and right adjoints just in terms of homotopy colimits and limits over groupoids. So this is kind of the base case that we need to do for everything. And so so let's consider the case where G is a group. Okay, so then your left adjoint C lower shriek X, that's what's known as the Borel construction. So you've got in this case G is a group, X is a functor from G to spaces, but that's kind of just the same thing as a space with an action of G. And so we can take this EG plus. EG, remember, is the universal space. It's a contractible space with free G action. Can be constructed by simplicial methods. So it's got this EG space, but it's basically a space with a property that EG mod G is BG, classifying space. So anyway, we take this EG and then we take EG plus and we smash it over G with our space X, and that's the Borel construction. That's the same thing as the homotopy colimit. On the other hand, the right adjoint, C lower star X, is a homotopy fixed point spectrum. So you take the same contractible free G space, EG plus, you look at the space of G equivariant based maps from EG plus to X. That's your homotopy fixed point spectrum. So and so kind of interesting thing that we have here is that you can look at what's this homotopy groups of C lower star, C upper star, C? I mean, so C upper star E is just E with trivial E action, and C lower star, C upper star E is the homotopy fixed points. So that's so it's G maps from EG plus to E, but G is acting trivially, so that's just the same thing as F BG plus, well, right, as EG plus EG mod G plus comma E, right? But the whole point about EG is it's kind of the space such that EG mod G is BG, so this is F of BG plus. Okay, and so yeah, if we look at the pi k of this, so that's pi k of F of BG plus E, which is maps from the kth suspension of BG plus to E, which is, yeah, so that's a minus kth cohomology group. And so, so the homotopy groups of this C lower star, C upper star, that's regraded E cohomology of BG. And so the fact that C lower star is the same as C lower shriek, that's going to tell us a bunch of stuff about the structure of this ring. So we'll return to that theme later. Okay. So now I want to kind of compare that with some things about representation theory. Okay. So suppose I've got a representation of G, so that's an element of this category curly VG. So if I've got this V, then I can just take, and so you've got your C lower shriek V, so that's V crossover G, EG, and that has a projection down to a point crossover G, EG, which is EG mod G, which is BG. So you've got this space over BG, and this is actually a vector bundle. Right? It's easy to see that's a vector bundle. So a representation of G gives us a vector bundle over BG. And if you remember the complex K theory, KU upper 0, BG, that's the that's basically closely related to classification of vector bundles over BG. So this representation gives us an element of this K theory, which I'll call phi of V. And so using this, we've got this representation ring, RG, and you've got a map from RG to KU0 BG. So remember, RG is virtual representations, kind of formal differences of representations, but this KU upper 0, that's a ring, so you can subtract. So you've got sort of formal difference, V minus W, you apply phi to it, phi of V minus phi of W as an element in this thing here. Okay, so we've got a map here from RG to KU upper 0 BG. And there's not going to be any infinite groups anywhere in these terms. So as I said at the beginning, in this series of talks, we're talking about strict ambidexterity, where the left adjoint is the same as the right. And if you try and do stuff with compact Lie groups with positive dimension, then you don't get that. Even in the most basic sort of thing about the Witt-Müller isomorphism, you have to put in the adjoint representation of the Lie group on its tangent space. So you get a kind of twisted ambidexterity, not just a direct isomorphism between left and right adjoints. So for that reason, we're not doing any of that. Okay, so here, it may be that there's some way of adapting the story about ambidexterity to those cases, but that would be a different. No. So in these talks, everything is all groups are finite. So here, Seagal theorem, you take this representation ring and you complete it with respect to the augmentation ideal. Actually, yeah. So here I've written this in terms. If it's just a group, then you just say the augmentation ideal. You've got the map from RG to Z. For a general groupoid, you have to just say something just a tiny bit different because you've got a representation of a groupoid. It might have different dimensions in different places. But anyway, there's an obvious analog of an augmentation ideal. You complete with respect to that. RG completed this augmentation ideal gives you the K theory of the classifying space. Now, how's this related to Morava E theory? I said we're going to do some stuff in Morava E theory, but as I think, as Stanza mentioned earlier this morning, Morava E theory at height 1 is just the same thing as p-adic K theory. So let's just look at the case where G is a finite P groupoid, just to make life simple. Then the conclusion is that the E theory of BG, where E in this case is just a p-adic completion of complex K theory. E theory of BG is just a P completion of the representation ring. And so, as I said, we're going to have these ambidexterity theorems in the Morava E theory. But we've already mentioned that there's some, these kind of quite elementary and classical ambidexterity theorems for representations, and they're kind of tied together by this kind of a Seagal story. Right, so I mean, well, the point is that, yeah, the reason I said a P group or a P groupoid is that, you know, if G is a P group, then the augmentation ideal is kind of basically the same as the ideal generated by P. So here's just a little side remark about, you know, so we're going to do some stuff, we're doing various things with ambidextrous junctions, and we need to kind of do some formal manipulations with these junctions. It's nice to have a kind of little graphical calculus for dealing with this. And I guess you know, many people are familiar with this kind of picture that you can, you've got a sort of graphical calculus for dealing with dualizable objects in a symmetric monoidal category. And this is kind of similar, but a little bit different because we're dealing with functors. And you could kind of think about a situation where if you've got a category of endofunctors, functors from one category to itself, then that's a monoidal category, you know, under composition, but not symmetric monoidal. And then here, actually, we don't just have functors from one category to itself, but functors between various different categories. But you can still do a kind of nice graphical calculus. So yeah, I mean, let's suppose we've got an ambidextrous junction here. So you've got your two categories, C and D, and then you've got two functors, F and G, you're supposed to have two adjunctions. So if we just kind of write this in more classical notation. So yeah, one adjunction, you know, you've got epsilon from GF to 1 and eta from 1 to FG. And then you've got these triangular identities for an adjunction. So here, what have we got? Here you've got, this is kind of eta F, and then this is F epsilon. And the composite here is supposed to be the identity. And then there's another triangular diagram for this adjunction, and then there's two other triangular diagrams for the other adjunction, because F and G are supposed to be adjoint the other way around as well. And we don't want to draw pictures of those, okay? So over here we have this epsilon GF to 1, so that's supposed to be this picture here. So kind of horizontal lines of the functors, and we're composing, you know, writing everything in this direction. So this means G composed with F here, G on the left and the F on the right. So these two dashes here correspond to that. And then your GF is supposed to go to the identity functor. The identity functor is just kind of represented by nothing at the top of this picture. And then your epsilon goes between them. So it's kind of all these natural transformations of these kind of solid regions in the plane. And there's epsilon like this going from GF to the identity, and epsilon prime from FG to the identity. And similarly, eta, yeah, and then, you know, there's all these colors. The functors are always red and blue. All these horizontal lines representing functors, they're red or green to indicate F or G. Categories, kind of orange or blue. So C is orange and D is blue, and this is epsilon, you can tell, is going to the identity functor on C because you've got an orange on the top. And then you know, in your F, the target of F is here, target of F is D, and the source of G is also D, and those D is blue, so that this little blue arc here is indicating that. And then if you look at this kind of triangular diagram here, you first do eta F, and then F epsilon. So remember, yeah. So this is remember F and G are both F is both left adjoint and right adjoint to G. So you've got to have the other co-unit like that for the other adjunction. And yeah, each of these 4 triangular diagrams, they correspond to a kind of like bent thing like this. You know, one way around the diagram corresponds to one of these kind of bent things, and then the other way around is the identity, which is a straight cube. So the kind of graphical rule is just that you're allowed to straighten any of those things. Okay, so let's go back to talking about finite groupoids. Okay, so mind our basic definitions. Groupoids are a category, and all morphisms are invertible. So typically, objects will be called small letters like A. So object A and then GAA, the morphisms from A to A in the category, that's going to be a group because everything's invertible. And basic consequence of that, if there exists a morphism U from A to B, well then composing with it gives you a bijection from GAA to GAB. So in particular, the size of GAB is the same as the size of GAA. And also conjugation by this U is going to give you a group isomorphism from GAA to GBB. So, objects in the same component have isomorphic automorphism groups. Instead, you've got a group. You can regard it as being a groupoid with one object. When we say the groupoid is finite, well, I don't necessarily mean that it's only got finitely many objects. That would be an inconvenient restriction, but I do mean there's only finitely many isomorphism classes of objects, which is basically as good. And then also that GAB, each morphism set GAB has got to be finite. But by these principles here, you know, GAB has got to be finite, so it's the same as saying that GAA has got to be finite for every A, and you can just test that on one object in each isomorphism class if you want. So if you want, what you can do is you just pick one element in each isomorphism class, gives you, and so we're assuming that there's only finitely many isomorphism classes, so you just got to list A1 up to AR, one element in each isomorphism class, and then you get if we put GI as the automorphism group of AI, so that's a finite group, which we can consider as a one-object groupoid. And then you just take the co-product of these guys, G1, co-product of G1 up to GR, co-product in the category of groupoids. That'll be equivalent to the original G. So that means that, basically anything, as I said, that you want to do with finite groupoids, you could reduce to questions about finite groups, but in order to do that, you do have to kind of choose these representatives, which can be a kind of awkward and unnatural thing to do. And as I said, our kind of goal is to get to this saying a bunch of stuff about infinity groupoids or pi-finite spaces. And, so the lead up to that, it's going to be good to think about everything in terms of groupoids. Notice also that in the other kind of extreme, the sort of opposite extreme is you've got a set, you can consider it as a groupoid with only identity morphisms. So a set, and there's no morphisms from X to Y unless X is equal to Y. And if X is, and the only morphism from X to itself is the identity. And so it's convenient that by working with groupoids, we've got this category that contains sets and also contains groups. And so a groupoid is, so a set is a groupoid with only identity morphisms, like I said. So it's useful to consider when is a groupoid equivalent to a set, right? When is a groupoid equivalent to a one-point set? We say a groupoid's contractible, and we've written this, so. you've got a non-empty groupoid and all morphism sets have size 1, then that's equivalent. It's pretty easy to see that means that the unique functor from G to the terminal category is an equivalence of categories. And that's what we mean by saying it's contractible. And groupoid's equivalent to a set if and only if every component is contractible. And to say every component is contractible is the same as saying that there's never more than one morphism between any 2x and 1. Okay, so let's go through it. Yeah, so we had a brief thing at the beginning about representations of finite groupoids, so let's do that again a bit more slowly. So, so curly A, category of abelian groups, AG, category of functors from G to A. And so the basic notation we'll use for this. So A is going to be an element of this category, so that's a functor from G to abelian groups, and the value at a particular object is going to be called A subscript X. And then if you've got some U from A, oh, it's a typo, that U should be in GXY. Okay, so if U is in GXY, a morphism from X to Y, then it will induce a map from AX to AY, which we're going to call U lower star. Basic operations we can do, just do any operation you want point-wise. So, so direct sum of two objects, you just take a direct sum at each level. Tensor product of two functors, you just take the tensor product at each point. And there's kind of internal HOM thing. So HOM underline AB, that's an yeah, that's a typo. That should say GXY instead of GAB. So HOM AB is just a set. It's just the this would just be this. HOM underline AB is this kind of internal mapping object. That's in it. So this is itself a functor. And so it's internal mapping object, and you just do HOM at each X. And then the kind of tensor unit, the thing, the identity object for the tensor thing is just a constant functor with value Z. And so we've got the unique functor from G to the terminal category. C upper star is the functor that just sends an abelian group to the corresponding constant functor. And left adjoint is just sends one of these A's to its co-limit, and the right adjoint sends one of these A's to its limit. So as I said, these kind of limits, for a general functor Q, then the left and right adjoint can be described by the so-called Kahn formula as co-limits over auxiliary categories. So you've got this Q here and some object B and H, and you want to look at this comma category, which I'm going to write as Q down arrow B. So the objects are pairs where you've got an object of G here and a morphism from QX. You've got object X in G, and so QX is in H, and you've got a morphism from QX to B, which you're going to call little v. So pairs like that, those are our objects. And we draw the picture. So yeah, you've got an object you can kind of think of as, so this is over happening in G, this is happening in H, and you've got And then for morphisms, you've got your x1 here and your x2 here, and then qx0 going to by v0 to b, qx1 going by v1 to b, and so you have a morphism between this first object and the second object. You're supposed to have a G here, which is on the left-hand side in the category big G, which is supposed to make this diagram here. That's your comma category. And notice here we're working with groupoids, so this is necessarily an isomorphism. So I could turn it around. If we were working with general categories, then you'd have to kind of consider, you'd have to distinguish between a kind of left comma category and a right comma category, depending on whether your morphism is going from Q or into Q. But because we're working with groupoids, we don't have to bother. So this is a category of, there's a very similar category of pairs where you've got a pair XW, and now your W is a morphism the other way from B to QX. But it doesn't matter. But yeah, these two categories are isomorphic. And so if I've got some A here, a functor from G into abelian groups, then I can just kind of compose with the projection, get the functor which sends one of these pairs XV just to AX. This gives a functor from the comma category to abelian groups, and the co-limit and limit of that functor those are the values of the left adjoint Q lower shriek and the right adjoint Q lower star. Okay, so this is this is called the Kahn formula. The Kahn formula kind of works for the left and right adjoint of a pullback functor. In complete generality, you don't you don't really need a groupoid, but if we didn't have groupoids, then the left adjoint would be defined using this version, and the right adjoint would be defined using that version, and that would be a little bit different. But because we're doing groupoids, we can just use one version. It's the same thing. In any context where we know that you've got this kind of ambidexterity for the limits and co-limits in this situation here, then we can just apply that to these comma categories, and we get get ambidexterity for Q lower shriek and Q lower star more generally. Okay, so then we wanted to have a morphism from the left adjoint to the right adjoint. So let's examine how that works. Okay, so you've got one of these A's, a functor from G to abelian groups. You've got a pair of two different objects, X and Y. So I'm going to define, so if I've got any morphism U from X to Y, then it gives me a U lower star from AX to AY. And I've got finitely many morphisms because we're dealing with a finite groupoid. So I can just take all these U lower stars and add them up. We're dealing with abelian groups, so adding homomorphisms, there's no issue with that. So just take the sum of the things induced by all possible morphisms, and I call that nu prime XY. And now it's pretty easy to see that this diagram here. So we've got some. I said I've got my G is from X prime to X, and my H is from Y to Y prime. Right. Now, if I've got a U here, then of course I've got HUG here, and this construction here is just going to give me a bijection from GXY, GX prime Y prime. And using that, we see that you've got this property here. The nu prime X prime Y prime is the same thing. That should be a nu prime there as well. Okay, so these kinds of things are compatible with composition on the left and the right. And so because it's kind of compatible with composition on the right, that means it's actually going, this map is actually landing in the inverse limit over the y's. And because it's compatible with composition on the left, this map is factoring out of the co-limit of the axis. Right? So we conclude from this compatibility here that there's a unique map from the co-limit to the limit, which has the property here, like this, that, oh, again, that's a typo. This thing in the middle is supposed to just be new. Write it here. Write it correctly here. So you've got this new here. So to give you, this is a map from a co-limit. So in order to say to understand what's happening with the map out of a co-limit, we need to see how it composes with the canonical inclusions here. To understand a map into a limit, we need to understand how it composes with the canonical projections here. And the answer is that this composite is nu prime x1. Okay. As I mentioned, so your left and right adjoint are the same on projectives. So let's prove that bit first. Okay, you've got so what are the projectives in this category? Well, the projective generators, the most obvious kind of projectives. Another type, but this should be called PA, not PX. So PA is the functor that sends X to the free abelian group on GAX. But that is the same, of course, as free abelian group on GXA, because GAX and GAX, just because it's a groupoid, you've got this inversion map that's bijection between those two sets. And using this description, the Yoneda lemma, you find that morphisms from P to A is isomorphic to the value AA. And using this second description and the Yoneda isomorphism, you see that homomorphisms from A to P, they just also biject with this value, with the value of the functor at A. And just take A to be a constant functor. So then that's, if A is constant, then maps from P to A is the same thing as maps from the co-limit of P to A. And if it's also maps into P are the same as the maps into the inverse limit of P. So from these things in the Yoneda lemma, it's pretty easy to see that both the co-limit and the limit of this P are just Z. So that means, well, what is this new? It's not kind of, from how I've said it here, it's not totally immediate that, what's new is a map from Z to Z. It could be multiplication by some other number, but in fact, it is just the identity. So you get just by checking through this construction, the details of this construction more carefully, you'll see that this is just equal to 1. So we find that on these projective generators, you're getting an isomorphism, and therefore you get an isomorphism on all projective objects. Okay, yeah, what if it's not projective? So we need to say something a bit more there. So let's consider this this kind of order functor, right? If G is a group, then you just want to consider the order of the group. If G is a groupoid, then you want to consider the orders of all the automorphism groups. So call that dx as the order of the automorphism group at X. And by what we've said previously, the size of every, if GXY is not empty, then the size of automorphism groups at X and Y are the same, and that's the same as the number of homomorphisms from morphisms from X to Y. So this is isomorphism, invariant on isomorphism classes. So now let's choose representatives of each isomorphism class, and then for each of these, you've got the map, got your limit, and then universal property of the limit, you've got a projection from the limit to the value at the function at the point AK. And then by the universal property of the co-limit, you've got a map from this AAK into the co-limit there. And so you've got, so this is giving you some maps from the limit to the co-limit, and you add them up, one for each isomorphism class. Yeah, it apparently depends on the list of representatives to be chosen here, but actually it doesn't. It's pretty easy to check that. And also, yeah, if you take a composite, you do rho composed with nu, or nu composed with rho, either way around. It's just a multiplication by this d. So, tiny bit to say about what it means to multiply by d, given that d might be a non-constant function, but in the case where G is a group and there's only one, or the case where there's only one isomorphism class, D is just a number and you're just multiplying by that D. And so in particular, if D is invertible in the relevant context, then your nu is going to be isomorphism. So it's an exercise. It's it's not like you just unwind. Yeah, you do just unwind the definitions. Okay. Yeah, and so so D is invertible. That you find that there's nu is an isomorphism, and between the co-limit and the limit. Yeah, when G is a finite group, yeah, this is just the standard isomorphism from the co-invariance to the invariance, just written in a slightly fancy way. Yeah, and it still works. So we did this just for co-invariant for co-limit and limit, in other words, for kind of functors to the terminal category. But by this thing with the comma categories and the Kahn formula, you see that for any functor Q from G to H of finite groupoids, we have this ambidexterity. So G, so remember that we can consider sets as groupoids, or finite sets, finite groupoids. G is equivalent to a set if and only if this D is equal to 1. And if D is equal to 1, then we don't need to divide by anything. And so the left and right adjoints are the same. And it's an exercise to see that, we look at these comma categories. When are the comma categories equivalent to sets? And that happens if and only if your Q is a faithful functor. So if Q is a faithful functor, then comma categories are equivalent to sets. And so you've got ambidexterity for the comma categories, and therefore by this Kahn formula reduction, you've got ambidexterity here for arbitrary functor, arbitrary faithful functor. Okay, I'm supposed to stop at 1/2 right? Okay, so I was expecting that I would go through this quicker, but never mind. Okay, so I'll stop there for today.
Questions, comments?
Yep. Yeah, that's what it is.
So is this a special case?
Yeah. Okay. I mean, the only thing that's special is that the left and right comma categories are the same.
Is this internal?
Yeah. So well, I mean here, yeah. So here I've defined what I mean by the tensor product, and then this Hom is it has the No, I mean the so so you've got well, I mean just that they're reduced to just the reduction to groups, right? I mean, yeah. So well, yeah. So I mean, what do you mean by classification? I mean, you want to the natural thing is to classify up to equivalence. When you're talking about categories, you want to classify them up to equivalence, and yeah, well, this is the classification, right? A groupoids up to equivalence is just the same thing as kind of families of groups up to isomorphism, and in fact, I mean, yeah, but I mean, pi naught g is just, yeah. I mean, here, I mean, in this case, I mean, pi naught g is just a set of size r, right? Your pi naught is just a discrete set, and the whole groupoid basically is just a family of groups parameterized by that set. So, sorry. Well, no, there's a set and there's one group for each point in that set. So, yeah, I mean, yeah. Okay, so yeah, right. So groupoid is basically a family of groups parameterized by a set. No, they don't have to be the same. Yeah, and so then, you know, the representation category is just the product of the representation categories of all the individual groups.
In the next slide, you define the new map. Oh, it might be in the slide after this. The map new from C shriek to C star. So here you said that, so for that C shriek to be the co-limit, we needed C to be the functor to the terminal groupoid, right?
Yep.
So are we working with that case? Because
yeah, that's what we're working with here. Yeah.
So C is the functor to the terminal groupoid.
Yeah, in this case.
But weren't we trying to prove this for a more general C?
Yeah. Okay. So you've got.
Oh, using the Kahn formula.
Yeah. So you Q from G to H, and then you've got. And then you've got a C, which maybe if you like, you can call CB there. And then, yeah, so then you want CB shriek.
Right, thank you.
Any more questions? So if not, let's thank the speaker again.